Hi Year 12s, this is question 4 of the recursive relations that we're working on. Okay, so this time our non-homogeneous part here shows that we're multiplying by 5 as we go from term to term, and so we know we've got to have power of 5 as our complementary function. So the complementary function here will be some arbitrary constant times 5 to the power of n. And now if we look at the non-homogeneous part, okay, we can see that we've got a multiple of 5 to the power n. So we might think that when we're doing our particular solution, okay, that we have a constant multiplied by 5 to the power n. Okay, but this doesn't work. Let's just try it and see what happens. So if we're going to substitute into our recursive formula, let's try the n plus 1th term would be a times 5 to the n plus 1. So let's substitute in. So we've got a times 5 to the n plus 1 is equal to 5 a times 5 to the n plus 2 times 5 to the n. So if we try and write everything in terms of 5 to the n, we've got 5a times 5 to the n equals 5a times 5 to the n plus 2 times 5 to the n. And if we look at all the coefficients of 5 to the n, we've got 5a is equal to 5a plus 2, but that means a could be absolutely nothing at all. There's going to be no solution that works for that. Okay, I suppose the only answer would be if a is 0. But if a is 0, then we don't have a particular solution, so it doesn't work. So if you end up discovering that your constant, if you've only got a single constant, is 0, then you've got a failure case. Okay. Okay, now in that situation all we do is we just multiply what we would normally guess by n, and everything turns out fine. Okay, so I'll do this in red just so that it's easier to see. So we're going to guess our particular solution is an 5 to the n. So if we wanted the n plus 1th term, we'd have a brackets n plus 1 5 to the n plus 1. So we need to substitute that into our recursive formula because the recursive formula has to work for any solution. So let's try it. So we've got a n plus 1 5 to the n plus 1 is equal to 5 to the n, and then plus 2 times 5 to the n. So if we write everything in terms of 5 to the n, again it's easier to figure out what a will be. So we have got 5an times 5 to the n plus, and then we'd have 5a times 5 to the n is equal to 5an times 5 to the n plus 2 times 5 to the n. So if we're comparing coefficients of n 5 to the n, then we're going to get 5a is equal to 5a. So again, that doesn't help us because a can be anything. But if instead we compare coefficients of 5 to the n, then we've got 5a is equal to 2. We've got something to work with there. So a is 2/5. That means our particular solution is going to equal 2/5 times n 5 to the n, and we could write that as 2n 5 to the n minus 1. Okay, so now we can combine our complementary function and our particular solution to get our general solution. So the complementary function, a times 5 to the n, and then our particular solution is 2n times 5 to the n minus 1. And we can use the initial conditions to get our final solution. So when n is 0, u is a fifth, so we pop that in, so we've got 1/5 is equal to a times 5 to the 0 plus 2 times 0, 5 to the minus 1. So this term becomes 0, the 5 to 0 is 1, so that means a is 1/5. So the final solution is going to be un is 1/5 times 5 to the n plus 2n, 5 to the n minus 1. So again we can write that as 5 to the n minus 1 plus 2n, 5 to the n minus 1, or if you like factorising, 1 plus 2n. There we go. Alright, now we're going to check that that's correct on our calculators. So I'm going to put in the recursive definition first. So we have 5an plus 2 times 5 to the power of n. Okay, and then our nth term formula, our closed form. So we've got 1 plus 2. Now it's going to be n plus 1 because we're using bn plus 1 instead of bn. Okay, so n plus 1. Alright, times 5 to the power of, and so this will just be n. Okay, set. We're going to start our counter at 0 again. Alright, and we want our very first term to be 1/5. Okay, and let's check. So, yep, if you look, that our recursive definition matches our nth term.